Okay, hello everyone. Welcome to today's lecture. Please confirm that you can hear me and see my screen. Thank you. Thank you. Okay, uh, in last lecture, we started discussing about how we can write the assembly language programs. Actually, we had a look at very basic information, like, for example, how a program executes, when a program executes, what through what different components of the processor it goes through. And then we also had a look at, or we talked basically about that every instruction is at the end of the day converted into the binary code or the machine code. So there is a fixed binary code for each operation. And then we also need to know where are operands, and those operands can be in registers or they can be read from memory, right? So we had a look at examples about adding two numbers, right? So today we will continue our discussion of how to we'll continue learning the assembly language, okay? For at Mega 328 microcontroller, 328P microcontroller. So so remember last time we had a look at add instruction. Now let's make use of that add instruction through an exercise. So we want to write a program which calculates the sum of numbers 19 and 95, right? So how can we write the program? So what we can do is that we can first put the value of 19 in a register. Remember last time we said like there are 32 general purpose registers here on the right side in the register file, right? So what we can do is that we can put the value of 19 in any of these registers. Uh, uh, I'm not sure. Let me double check with the previous lecture slide. What was the restriction on if there was any restriction on load immediate instruction or not? I guess there was. Yeah. So we can load the value in register 16 to 31. Okay. So we can load the value of 19 in any registers ranging from 16 to 31, right? So what we can do is that let's say we put the value of 19 in register R16 and we put the value of 95 in R20, and then we want to add the content of these two registers together and put the result back in R16. So if we successfully do that, then we can get the sum of these two number in register R16, right? Now, this is like, if you just look at the comments, so this is like our plan, what we want to do, right? But how we actually do it and achieve it in assembly language, or what instructions we need to use. So remember last time we also talked about load immediate instruction, right? So what we can do is that we can say we can use the load immediate instruction to put the value of 19 in R16, right? And then in next instruction, so this is one instruction, okay? And one instruction is executed in one cycle. Uh, so here, then in the next instruction, we are saying put the value of 95 in R20. Load immediate. Immediate means load this immediate value of 95 into register R20. Now R16 has 19, R20 has 95, and then we can use the add instruction, which we have seen in last lecture, to sum the two numbers. So when we say add R16 R20, the content of these two registers will be added and placed in R16. So in this way, we will get the result of addition in register R16. Okay. Any questions? Okay, thank you for confirming, having no questions. Okay, now let's go to the next example. Write a program that calculates 19 plus 95 plus 5. Okay, let's use it as an exercise. Do it on your notebooks, and you have 1 minute to do that. Okay, and let me know when you are done. And as always, I'm also doing exactly same thing on my notebook. Let me know when you are done. Thank you. Thank you. Good. Yeah, nice. Yeah, nice, nice, nice. I would love to see some new names, like new names being those which normally don't appear in the list of like reporting done or not done. Okay. Thank you. Thank you. Okay, so here is the example, right? This is how we can do. You can put 19 in one register, 95 in another register, 5 in another register, and then sum all them together. So I'm putting 19 in R16, 95 in R20, 5 in R21, and then we are saying, okay, now add R20 and R16. So R20 is 95, R16 is 19. So we get the sum of 19 plus 95 in R16, right? And then we are saying add R16 with R21. So we will get the result of 19 plus 95 plus 5 in R16. And this is also clear from these comments. One, one clarification, you can use here any registers. Like for example, this example or this solution I used R16, R20, R21. You could have used also R16, R17, and R18, right? So it's fine. As long as the register is uh, the range name of the register is like R16 to R31. Okay. Okay. So now write a program which calculates exactly the same thing, 19 plus 95 plus 5, but efficiently. What do we mean by efficiently? Efficiently mean that here we are using how many instructions? We are using 5 instructions, right? So the question is, can you do the exactly same thing, let's say using 4 instructions? Give it a try. Like, can you reduce the number of instructions by one? Can you save one instruction but get the same summation? You have 1 minute to do that. And it's fine. If you are not able to do that, it's fine. I mean, but I just want you to give it a try or think about it. Okay, let me share the solution. Okay. Oh, mm, actually, sorry, the statement of the question was not correct. It's not efficient. It's just a different order of doing the things. So this is incorrect. Okay. So, and I was thinking like when I gave you the exercise, and I was also thinking to do it on my notebook, and I couldn't think of a way to reduce the instruction. So then now when I look at the solution, I found my mistake. The mistake is actually in the problem statement, right? It is just a different way or different order of the instructions, but the total number of instructions are same. So here what you are doing, you are loading 19 into 16, 95 into 20, and then summing them together, and then loading R25, loading 5 in R20, and then summing it to R16. So total number of instructions are same, but there is a one difference. What is the difference? The difference is that how many, can anybody tell me how many different registers are used in this first example? Anybody? How many different registers? Three, yeah. 16, 20, and 21. But in the second example, we are using only two different registers, R16 and R20, right? So not less memory. You can say we are using less number of registers. And if our program is using relatively less number of registers, it's mean it is putting less pressure on the registers. Okay. So lesser the pressure on the register, more efficient it is. Why? Because then it's mean that other registers, for example, here R21 is not used in this example, right? R21 is not used. Now R21 can be used for some other purpose by the same program, right? So we are saving one register. Okay. So it is like it puts less pressure on the registers. One register less. And it's a good practice because then it helps in other things, for example, in context switching, which we are not going to talk about at this point, or when you are calling functions and you need to save registers. So all the registers which the caller function is using, they need to be used. They need to be saved in memory. So if the caller function is using lesser number of registers, then you will need to save lesser number of them registers in the memory. If more registers are used by the caller functions, then more registers will be needed to be saved in memory, which means more time will be taken, right? More time will be consumed. So it's always better to use the smaller number of registers if you can. And yes, definitely, if you can rewrite a program by using lesser number of instructions, that is also how to say, preferred feature, or a nice feature of your program. But in this example, we cannot reduce the number of instructions. Okay, let's continue. Okay, arithmetic calculation. So last time we have seen like add instruction and load immediate instruction, right? Now we are going to have a look at subtract instruction. So its syntax is very similar to what we have seen in add. The only difference is that instead of using the opcode or operation of add, we are using sub. So sub indicates subtraction. Okay. So here what will happen is that source content of the source register will be subtracted from the content of the destination register, and the result of subtraction will be saved in the destination register. And these RD and RS, they can be any of 32 registers. And as a result of the subtraction, your status register bits are affected. How? We will talk about them later. But at this time point, it is sufficient just to know that as a result of subtraction instruction, the bits in this, the values of the bits in this status register, they are affected. So here you have 8 bits like C, Z, N, V, S, H, T, I. We will talk about them later, but just keep in mind that the values of these bits can potentially change after the execution of subtract instruction or even after the execution of add instruction. Okay. So here is an example. Sub R25, R9. So content of R9 will be subtracted from R25, and the result of the subtraction will be placed in R25. Okay. So R25 is both a source and a destination, but R9 is only a source. Another example, subtract R17, 30. So content of R30 will be subtracted from that of R17, and the result will be placed in R17. Okay. I think it is pretty straightforward. So, but if you have any question, feel free to stop me. Another instruction which we have in the group of arithmetic set of instructions is increment instruction. And this instruction is different from add and sub in the sense that it takes only one operand, and that is indicated as RD register. So what does it do is that if you execute this instruction, the content of the RD register will be incremented by 1, and the result of increment or incrementing the value will be stored back in the same register. Okay. So here is example, increment R25. So whatever value of R25 is, it will be incremented by 1 and put back in the same register. Okay. So here is just an example of the machine code or the binary code for the increment instruction. So remember we said that machine code of any instruction is broken down, like typically broken down, or at least in Atmega 328P, it is broken down into two fields, opcode and the operand, right? So, but from one machine code of one instruction to the machine code of other instructions, it varies. The location of the opcode and the operand bits, they vary from like one instruction to the other. So here, in case of increment instruction, the least significant 4 bits and most significant 7 bits, they are reserved for the opcode. And the opcode they have is shown here. You can see like what is the value of opcode. You can convert into the hexadecimal if you want, right? So here it will be 3, this will be 9, and this will be 4. So in hex, it will be 0x493 will be the opcode of the increment instruction. And the remaining 5 bits, they are used to specify any of the 32 general purpose registers, right? So since we have 5 bits, so how many registers we can specify? 2 raised to power 5 is equal to what? 32, right? So when all of these D bits are 0, it's mean we are specifying the register 0. But if all of these bits are 1, D bits are 1, it's mean we are specifying the register 31. Okay. If any confusion at any point, stop me. Okay. Decrement. It is like complementary instruction. I mean, it does what is done by increment. It does exactly this opposite. So you specify a destination register, and this instruction reduces the value by 1 and puts the result back in destination register. Here is an example. Decrement R23. So whatever current content of R23 is, it will be reduced by 1 and the result will be placed back in R23. Okay. And again, if we look at the machine code of decrement instruction, it will look like this. So again, you have these 4 bits and 7 most significant bits reserved for opcode, and the middle 5 bits, like from like these 5 bits, they are reserved for the operand. Okay. And what is the, if I convert it into hex, so it will be equal to what? 9 and 9 and 4. So the hexadecimal code is 0x499 for the opcode of decrement operation. Okay. Can these also use all 32? Yes. So all 32 register. Actually, you can infer that information from these bits because these are 5 bits, and again 2 raised to power 5 is what? 32. So you can specify any of the 32 general purpose registers. Okay. Any questions before I go to the next slide? No, thank you. Then let's continue. Okay. So data memory of at Mega 328P, actually it is that what is the whole address range of the data memory is divided into 4 sections, right? So when I say whole address range, it's mean, let's say this is your whole memory, right? And I think it is 32K. I am not exactly sure. I guess it is 32K, right? So if that is the case, um, so first 32 bit locations, our first 32 addresses, like from 0 to 31, they are for your 32 general purpose registers. Next 64 locations, I'm just writing here 64, okay? Next 64 addresses, they they point to the 64 IO registers. IO registers are those which are used for input for access which are used when you are doing input operations or output operation, which means you are reading input from some device or you are sending data to some output device. Okay. We will talk about that later. At this point, don't worry about that. It is just sufficient for you to know that the next 64 locations or next 64 addresses, they point to the 64 IO registers. Okay. Now, beside that, there are the next 60 instructions, and the next 160 locations, they point to extended IO registers. Okay. Uh, so why we are like differentiating between like 64 IO registers and next 160 extended IO registers? There is a one main difference. So there are some special instructions which can be used only with those registers which are in this address range, like in this 64, like from 32 to 63. You can add it 32 to plus 64, whatever number it is. Okay. So there are some instructions which can be used only with the registers pointed by these addresses. Extended IO registers, these are also input or output device registers, but those special instructions, for example, let me give it the name to those instructions so that it is like more meaningful to talk about them. So like in and out. So these I will later explain what in instruction does and what out instruction does. But you can use in and out instructions only with the registers which are in this range, right? IO registers. And you can, the registers in this range in next 160 locations, they are also registers related to input or output operation, but you cannot use in and out instructions on these registers. Okay. And the next locations, 2048 locations, they are for static RAM. So it is for holding data. I think I'm wrong. The total locations are not 32K. Okay, well, I will check it and then confirm you, but let me not feed you the information I'm not sure about. So the address range is for the 32 registers, it is 00 to 31. So when you convert 31 to hexadecimal form, it will be 1F, right? Thus, address range for the next, so the 64 locations pointing to IO registers is 20, which is basically 32 in decimal. When you convert into hexadecimal, it will be 20, and 5F. So 5S, you can actually do the math. So 32 plus 64 is 96. So this is basically 95. So this is decimal is 95. When you convert into the hexa, it will be 5F. Why 95? Because we first location has address of 0, right? Otherwise, if you add 32 and 64, you will get 96, right? And then the address range of the 160 extended IO registers is 00 to 60, 0060 to 0x00FF. You can again do the same thing, 96 plus 162, and you can convert and you will find it. Okay. And this is the address range of the uh, static RAM where you can hold your data. Okay. 0100 to 08FF. Any questions? Okay. Uh, no, okay. Thank you. Okay, so what is this about data address space? Okay, so how the CPU accesses all this data address, all these locations in the data address space. So data address space basically is all the locations, all the addresses in your possible address range, which is basically start, if I go back, which is starting from 00 to 0x08FF, right? So this is your total address range. It is also known as address space, right? So how CPU accesses it, right? So these general purpose registers, they are within the CPU core. Remember, we are talking about at mega 3 to 8P, and everything, all of this is on a single core, right? Sorry, single chip, right? But when we say general purpose registers, they are inside the CPU. It's mean that they are part of the CPU module. Okay. And then on the chip, you have a data bus and also definitely address bus and control bus, which connects the CPU with RAM, EPROM, timers, everything, right? So this is how the CPU accesses general purpose registers. General purpose registers are on the same module, but if you want to access uh, RAM locations or IO registers, right? How registers will be accessed. So, for example, if you want to access the IO registers of some port, like there are three ports, we will talk about them later on your Atmega 328P port B, C, and D, and each one of them have their own registers to configure them or to use those ports, right? So how CPU will access those registers through these buses. But what will be the mechanism? CPU will place the address of those registers. So for example, if let me go back. So for example, if you place the address of 0x0020, right? So then uh, the ports, they will know that whether this, for example, port A will know, port B, C, and D, each one of them will know whether this address is for them or not. So because it's mean that like the register within port B has its own address. Registers within port C, they have their own distinct addresses. So using addresses, you can specify which address CPU want to access, right? So, and how we do that, as we have seen in earlier slides, are explained in earlier slides, by using address buses, data bus, and control bus. This is the same table which we have seen in the previous slide, specifying the address ranges for all of them. 32 registers, general purpose registers here. 64 IO registers, they are like registers of the ports, or they are registers in the interrupt unit, or they are registers of the timers, or they are registers of some other peripherals which are not shown here. For example, SPI port. Okay. IO is 160 extended IO registers. They are also distributed among these devices like timers, interrupt units, port, other peripherals. And internal T is 2048 cross 8 RAM. It is this one, right? Okay, let me get rid of these markings or drawings. Okay, now uh, we have talked about the address range and how that address range is divided into four sections, let's say registers, 32 general purpose registers, IO registers, extended IO registers, and then SRAM, right? Now let's see how we can move the data from an address into a register, right? Remember, we said that all of these 32 registers, sorry, let me use pointer. 32 registers, IO registers, extended IO, static RAM locations, all of them have a specific unique address, right? So let's say I want to load data which is available at a specific address into a register, right? So how I can do that? By using load direct data from data space, load direct from data space, right? Or LDS instruction. Okay. So what is the syntax? So first you write the LDS, which is like, acronym or acronym for the load data from data space. And then you specify the destination register where you want to put the data, and address from where you want to read the data. And so this is indicated by when you put a bracket inside around an address, it's basically mean that it is a memory address. It's mean that they read the value from the memory address specified in within the brackets and place that data in the destination register. If I remove these brackets, then it will mean simply load the address in the destination register. But if I use these brackets, then it's mean that I'm saying don't load the address in the register. Actually load the data which is available at that address into the register. Is it clear? Okay. Okay. So now let's have a look at the example then. So when you write load, I will read it as LDS, okay? LDS R1 0x60. So you are saying load the data from the address 0x60 into R1. Remember, it is not load immediate, it is load S, okay? So we are loading the data from this address into the R1 register. Now, what is 0x60? 0x60 is the address of the first register in the extended IO register range, right? So we are saying that load the data from this IO register, extended IO register into R1. Okay. Later we will see a table which will actually tell us that what is the name of the register available at this address. Okay. Let's not worry about that at this time. Okay. Okay. So just like we want to, like we can load the data from an address, memory address or an address into the register. In the same way, we can move the data from a register back into a memory location or to any location for which we know the address. Again, let me uh, wait. Where is eraser? Yeah, yeah. So if we want to do that, which means we want to put the data from a register into a memory location, right? So for that, we need to use the store direct to data space instruction or STS. Okay. And what is the syntax? You first write the name of the operation or acronym, and then you write the address where you want to put the data, and then the after comma you put the name of the register from where you want to pick the data, right? So this is what will be achieved. The value of the register will be placed in memory at the given address. Okay. Again, these brackets indicate that we are moving the data into the memory at the given address. Okay. Now, here is an example. When you say STS 0x60 R15, so what you are saying is move the value of the register R15 into the location which is pointed by address 0x60. So 0x60 is actually the address of first register in extended IO range, right? So we will be moving the content of the R15 into register, whatever register is pointed by this address 0x0060. Okay. Okay, now let's have a look at an example to make sense of what we have seen in previous couple of slides, like LDS instruction and STS instruction. Okay, so let me just erase them. Okay, so write a program which stores 55 into location 0x80 of RAM. Okay, let's first have a look at an example, then I will give you an exercise. So we want to store 55 into the location 0x80, but we cannot directly move the immediate value of 55 into the memory at location of 0x80. That is not possible. There is no such instructions in NetMega 328P microcontroller. Okay, so what we need to do then, we need to first load 55 in a register and then move the value of that register into the memory location 0x80. Okay, so that's why what we are doing, we are using first load immediate instruction, putting the value of 55 in R20, and then we use the store STS instruction, which will store the value of R20 into the into memory location identified by address 0x80. Okay, is it clear for everyone? So like, if you have this memory here, let's say, and you have like multiple location, and this particular location is its address is 0x80. So after the execution of these two instructions, the content of this uh, location will be 55. Okay. Okay, now let me give you an example. Write a program that stores the value of 20 in location 0. Okay, let me write a program that stores value of 20 in address 0x00F. You have 1 minute. Let me know when you are done. That could have just written as 0x since the leading zero. Yeah, that's correct, Nicholas. That's correct. Yes. Good. Cooked. Okay, good. Okay. So every will be the same. Here you will simply change it with let's say what was the value? Value was 20, right? And here you can keep R20 if you want, or you can change it with any register in the range R16 to R31. And then here will be remain same, and 0x80, which you will simply replace it with 0xFF, right? That's it. Can you use 0x0f as the address, or is it? No, the address is zero. The destination address is 0x00FF, right? I am confused why you are saying 0x0060. You can unmute yourself and you can talk. Okay, okay. I hope you got the answer of your question. If not, let me know. Okay, so now let me again erase all these annotations. Okay. And here we go. Now we need to write a program that copies the content of location 0x80 of RAM into location 0x81. Give it a try. You have 1 minute. Is everyone clear on the question? You just need to move the data from one location of the memory into another location of the memory. So like from 0x80 into location 0x81. Not move, copy. Thank you. Good, good. Done. Good, good. Thank you. So let's have a look at the answer here. So what you do is simply you use LDS load instruction to load from the static memory from address 0x80 into R20, and then you use STS store to the static memory at address 0x81 from register R20. Okay, so that's, I guess, kind of simple. Okay, now another example. Add contents of location 0x90 to content of location 0x95 and store the result in location 0x313. Give it a try again and you have 1 minute. In meantime, I can erase these markings here. Let me also do. Okay, nice. Good. I need one more done and then I will move. Okay, thank you. So we are simply moving the copying the data from address 0x90 into R20 from the other address 0x95 into register R21. We are adding them together and then we are using STS instruction to put the result in R20 to put that result from R20 into memory location 0x313. Anyone who is like not clear, if you have any question or if you don't understand something, let me know. Okay. 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 So what does following instruction do? Can anybody tell me? You can unmute yourself if you want to talk, or otherwise, it's up to you. Store the value in address. Store the value from address or to address to in R20. Okay. Put the value 2 into the register. No. It actually it doesn't put the value 2 in the register R20. It actually reads the value from the address 2 and puts that value in the register R20, right? But what if I say that this instruction copies the value from register R2 into R20? Will you agree with me or not? If I say that this instruction copies the value of register R2 into R20, do you agree with me or not? Okay. Why? Those who agree, why do you agree? And those who don't, give me also your reason. Okay. One student said that no, it doesn't move the value, copy the value from R2 to R20 because 2 doesn't have R in front of it. Okay. Those who think that it will move the value, yes, yes. So R2 is actually the address of the register 2, register R2, right? So when you say that move the data from the address 2 into the register R20, it is essentially saying the same thing like move the data from register R2 into R20. Why? Because remember, it copies the content of R2 into R20. Why? Because 2 is the address of R2. Here you can look. 0 is the address of R0, 1 will be the address of R1, and 2 will be the address of R2. Okay? Yeah, nice. So the address doesn't need to be specifically in hex. Uh, no, you can specify in whatever system you want. Like if you specify, let's say the address is, let's say 16. So you want to specify in decimal form, you can write 16. If you want to specify in hexadecimal form, you can write 0x10, right? And if you want to specify in binary form, then you will write 0b10000. Okay. Okay. I'm continuing then. Okay. Example, store 0x53 into the SPH register. The address of SPH register is 0x5e. Go ahead and try to do this example. You have 30 seconds. Thank you for letting me know. Let's wait for 5 more people to respond. Done. Okay. I have this bad feeling like 8 to 10 students are responding all the time. And right now we have like 22 participants, while the number of people enrolled in course is much higher. So like it looks like 60% students are not responding. So I mean, why I'm saying I have bad feeling because I know when I will get the student evaluation, at 6 week, I have we will have a student evaluation, not student, instructor's evaluation. So at that time, I know I will get this feedback that only same students are responding or not, the instructor is not interacting well with all the students. But now I don't know how I can make sure that all the students are participating. As I said, one way is to generate the polls, but during the lecture, if I generate the polls and launch them and then like close them, it takes time, it wastes time, so don't want to do that. That's why I will highly encourage you to do it on your notebooks. If you need more time, let me know. I will wait for you before moving to the next example or next slide. And even if you are like not able to solve, let me know. Even if wrong answers are correct, wrong answers are fine. I mean, don't worry about them like their correctness at this time point, right? Because we are learning, we are not in an exam. Okay. So even if you have wrong answers, uh, give it a try, share them with me. If you don't want to share with everyone, just select my name and from the list, and the message will be only I will be able to see your message, okay? And I will not call your names if your answer is wrong. I will try best to not call your names, okay? So, uh, yeah, so please do participate. Okay, so everyone is done with this. Store 0x53 into SPS register. Yeah. So this is like easy, right? Because we know that we can access the addresses using their addresses, or even we can access them using by name, their name. So, but here we are first, like we are learning in steps. So here we are first accessing the register using its address, right? 0x53. So what we are saying load load immediate 0x53 into R20, which is the address of the register, right? Sorry, this is not the address. This is the content which we want to place in the register SPH, right? So we are putting that value in R20, and then we are saying, okay, move the value stored in R20, move that value into the memory at address 0x5e, which is basically the address of SPH register. Okay. Okay, remember I told you we will see a table which will give us the name of the different registers and their addresses. So this is the table here. Let me clean it. Let me clean the screen. Okay. So the important thing here is that you have two columns, right? You have IO column, you have memory column, and a third column name. So this name column gives you the name of the register, right? And this IO column, it gives you the address of the, now all the IO registers, they have like you can address them in two different ways, right? Either you can address them using the IO address, or you can address them using the memory address. What does it mean, right? So for example, the memory address is what? The memory address of the first register. Okay. So the memory address of this first register is 0x0020, right? Convert it into the decimal form. What it will be? It will be 32, right? This is the address 32. Now look at this table. So 32 actually address points to this one, right? So IO, it is the in the IO register range, right? So in the IO register range, 32 is basically the first address. But if you look from the perspective of the whole memory, right, then it is the 32nd location, right? But from the within the range registers, its address will be 0. First location and its address will be 0. So remember, so if you look globally, I hope you guys are with me on this. If you look globally, the address of this uh, register is 32, right? But if you look only within IO registers range, it is the first IO register, so its address will be 0. Similarly, the address of the second IO register in context of the IO register range will be 1. But the address, if you look from the perspective of whole memory range, it will be 33, right? So here, so 33 will be definitely 0x21 in hexa, right? So the address of this first IO register, like in the whole memory range, is 0x0020 or 32, but in the IO range, it is 0. The address of the second register, it is 33, like in the whole memory range, but in the IO range, its address will be 1, right? So similarly, where is that SPH register, which we have used in the previous example? This SPH register, its address in the whole memory range will be 5E, but its address in the IO range will be 0x3E. Okay. Is everyone clear on this, like differentiation between two addresses? Address like in global memory range and address within the IO range. Okay, so from what you have shown us, we have to move data from memory to a register, then from the register to the memory, and can't copy data between two addresses directly. Yes, yes, Piper, we can't do that. It's not allowed. You cannot move the data from one memory location directly into another memory location, because there is no such instruction which supports the movement of the copying of data between two memory locations directly. So that's why you have to first move it into a register, and then from register into the destination memory location. Okay. Okay, everyone is clear on this slide, like this table, like we have for every register, we will have two different addresses. One address is its address in the whole memory range, and the other is the address its address in only IO register range. And see, the last address in the IO register range is 0xFF. This one. No, not why it's not. Is it X? No, not FF. 5F. Sorry, 5F. Okay. So this one. It is the address of the status register, SREG, which we will talk about, if not today, then in next lecture. Okay. So its address in the IO range is 0x3F, but its address in the whole memory from the perspective of whole memory is 0x005F. Okay. Now, remember, we said there are some instructions like in and out instructions which can be used only with the registers which are in this range. Sorry, in this 64 IO register range. So we can use those instructions in and out only with these 64 registers. Okay. And now we are going to talk about those instructions. So in instruction, so in it stands for input data from IO location. Okay. Or from IO register. Okay. So here is the syntax. In, you just give the name of the instruction or name of the operation, destination register where you want to put the data, and the source IO address. Okay. Remember, this is IO address. If the address is extended IO, you cannot use this instruction. If the address is in this range, 32 registers, you cannot use this instruction. If the address is in this internal SRAM range, you cannot use this instruction. Okay. So the requirement is that address must be within this range. Okay. And it should be IO address. Okay. It should not be memory address. What does it mean? It should not, you need to specify address using this column. For example, if you want to say read the data from register SREG into, let's say, R1, you need to specify this address 0x3f. Okay. So here is the example. In 0x3f R1, right? Now from table we know 0x3f is basically the address of IO address of status register. Again, I'm emphasizing this that this address must be IO address of the register, not the memory address. Okay. So you cannot use uh, sorry, my mistake. You must use 0x3f. You cannot use this address 0x005f in the instruction. If you use, you will get the error. Okay, when you will compile your program. And here is the other example in 0x3e R17. So 0x3e, we can go back and refer to the table. So IO, we look at the IO address column, right? We look for 0x3e address. It is basically SPH address. So it means that that instruction is saying move the data, copy the data from the SPH the register, IO register into the register R17. Okay. Okay. So just like in we instruction, we also have an instruction that performs the reverse separation, which is out. So it basically will write the data from a general purpose register into an IO register. But again, you need to specify that address of that IO register using the IO address, not memory address. Okay. So here is the syntax. You will first write the name of the operation, address of the IO register, IO address of the IO register, and read, which is basically the register from which you want to read the value. Okay. So what will happen? The value of that general purpose register will be placed in the uh, memory location pointed by this address. So here is example 0 out 0x3f R12. So value of R12 will be copied in the memory location 0x3f. So 0x3f is actually the IO address of register SREG, status register. So whatever value of R12 is copied will be copied in 0x3f. Okay. Now, if I write, for example, 0x, here if I write the address 0x005f, which is the memory address of the same register as reg, this instruction will not work. It will complain. Okay. Again, I'm emphasizing that you need to specify the IO address of the register with the in and out instructions. Another example, you are saying out the value of register R15 to the memory address, sorry, IO address 0x3e. And this IO address 0x3 is basically address of the SPH register. So R15 will be copied into SPH register. Is everyone clear on the about the concept of these two addresses for IO registers, memory addresses and the IO addresses, and everyone also clear on which addresses to be used within in and out instructions? If not, let me know. Thank you, thank you, thank you. Okay, so let me now clean this one. Okay. Okay, now previously we were using what we were doing, we were using the in and out instructions, but we were specifying the IO addresses of the instruction, sorry, IO addresses of the IO registers, right? If you want, you can also use the name of those registers in and out instruction instead of their IO addresses. Okay. So here, for example, previously we were saying 0x3e. We were saying out 0x3e comma R12. And 0x3 is the IO address of the register SPH. If you want, you can directly write out SPH comma R12, right? Same is true for in instruction. If you don't want to, because it makes your code more readable, right? So it gives you more sense. Like you can easily identify what register it is. So with in instruction, we were saying read the data from the IO register at address 0x3f into R15. And we can use directly the name of the register at that address, which in this case is status register. Okay. But keep in mind, when you will be writing, not like when you will be writing your assembly code in your labs. So if you directly use SPH and let's say SREG in your code, you will see error. Why? Because you need to add a header file. Okay. And if you cannot include header file, you actually need to use a directive which sets the value of SPH equal to 0x3. We will see how to do that. Okay, don't worry about that. But here, what I'm trying to highlight is that either you have to include the header file, or before using SPH, you have to equate SPH with the address of 0x3. Okay, we will see how to do that, but just be careful, okay, in your future labs. Okay, now let's do this example. Write a program that adds the content of the PINC IO register. So this is name of register. PINC IO. PINC is name of register. So add the content of the PINC IO register to the contents of PIN-D register IO register and stores the result in location 0x90 of the SRAM. Okay. Try to do this and you have 1 minute. Let me also do it on my notebook. Okay, thank you. You need to be happy, not sad for like doing the exercise. Or there are too much exercises, that's why you are sad. Okay, okay, okay. So let's have a look at the example. So we can use in instruction to read the value from PIN-C register and PIN-D register and put those values in two different registers, add them, and then you can use the STS instruction to move the result of addition into the memory location at address 0x90. So this is how we are doing. We are saying we are using the ins instruction, read the value from PIN-C register into the R20, read the value using in instruction from PIN-D register into R21 register, add the results, add the values together, R20 and R21. So you will have the result of addition in R20, and then you are saying store the value in static memory. from register R20 into the location pointed by address 0x90. Okay, I think it was easy. Okay, okay. So remember, we said like we have a the status register. Where is it shown? Here in the in your CPU, right? So this status register, we said it has different bits. So first, before talking about those individual bits, where it is located, it is the last register in your IO register range. Okay, so you can use in and out instruction with SREG. Okay, so now let's have a look at the individual bits. So there are 8 bits, and each of these bits, they are known as flag, right? And each one of them have name and their own significance. We will talk about them one by one, right? So the first one is carry flag, zero flag, negative flag, overflow flag, sign flag, half carry flag, temporary flag, and interrupt flag. Okay. At this time point, we will talk about only zero flag, carry flag, and half carry flag. Other flags, we will cover them later in the as we make progress in the course. Then we will cover them later. But now we will cover only these 3 flags. Okay. Okay. Now, yeah, before doing this example, let me explain. So carry flag is set, or maybe we can I can try to explain through example. Okay. So show the status of C, H, and Z flags after the addition of 0x38 and 0x2f in the following instructions, right? So what we are doing, we are first moving the immediate value of 38, 0x38 in 16, register R16, value of 0x2f in R17, and then we are saying add the content of these two registers, right? So when you will add, let me walk you through this, okay? So this dollar sign basically mean that the number is in hexadecimal form, right? So you convert it into the binary. What is the 4-bit binary of it? It will be 100, 1000, right? What is 4-bit binary of 3? It will be 0011. You do the same thing with the second number, 2f. So what is 4-bit binary of f? 4 ones. What is 4-bit binary of 2? 0010, right? Now you do the addition, right? So 0 plus 1 is 1. 0 plus 1 is 1 in the next bit position. In the next bit position, third bit position, 0 plus 1 is 1. In fourth bit position, 1 plus 1 is what? 2, right? But in binary system, we cannot have a digit of 2. So we convert it into the binary form, right? What is the 2-bit binary of 2? It is 1, 0, right? So we write the 0 here, this 0, and this one becomes carry. So we write it here on the top, right? Now we add the bits in the 5th bit position. 1, 1, 0. So 1 plus 1 plus 0 is 2. So again, we do exactly the same thing. So we'll get the binary of 1, 0. So we write 0 here and we write a 1 here, right? So 1 plus 1 plus 1 is what? 3. Now, when you convert 3 into the binary form, so in 2-bit binary form, it will be 1, 1, right? You write this 1 here in the summation part, and this next bit, it becomes a carry. So you write carry here, okay? So 1 plus 0 is 1, and 0 plus 0 plus 0 is 0. Is everyone with me until this point? Everyone understands how I did this addition in binary form? If it is not clear for anyone, let me know. Okay, thank you for confirming. So now, once we have the result, so once you do the addition, the value of these 3 flags, we don't worry about other flags at this point. The value of these 3 flags carry 0 and half carry flags in the status register. They they get updated depending upon the result of the operation, right? So how the carry flag is updated? Carry flag is updated if you have the carry out from the most significant bit position, right? Or if you have borrow in the most significant bit position. When you have borrow, when you will do subtraction. When you do addition, you don't have borrow, right? You have only carry out. So if you have carry out from the most significant bit position, like here, as I'm showing through this arrow here, then the carry flag will be set equal to 0. In this example, we don't have a carry out from the most significant bit position. So that's why the carry flag will be equal to 0. Okay? Because there is no carry beyond the D7 bit, this bit, right? Most significant bit. Now, the half carry flag, this flag here, this flag is set when there is a carry from the digit a bit 3 into bit at index 3 into bit at index 4. Okay, and we basically in this example we had a carry, right, which we are indicated by using this circle. So since we had a carry, so each flag or each bit in the S register will be set equal to 1. Carry was set equal to 0, half carry will be set equal to 1. And Z flag, it is set equal to 0 if the sum of result of addition is all 0. But result of addition is 0, but result of addition is not 0, right? So then Z will be equal to 0. Remember, again, Z flag is set equal to 1 if the result is equal to 0. If the result is not equal to 0, then Z is equal to set equal to 0. Okay. So in this example, our result was not 0. So Z flag will be set equal to 0. Okay. Is it clear how the addition instructions affects the Z flag, carry flag, and half carry flag? Thank you. Thank you. We have couple of minutes. Let me check if I should go to the next slide or not. Let's stop here. Next time we can actually start again from the same slide, from this slide, and then we will continue. Okay. Are there any questions? Today you don't have a quiz. So yeah, but in next lecture you have a quiz and get ready for that. Okay. So if no question, then that's all. Do we have to go to the lab if there isn't one assigned yet? Yeah, let me address this. Actually, I made an update, and I guess I also, if I remember correctly, I also made an announcement. What you can do is like, uh, okay, let me share my screen. What you can do is that go to the syllabus, right? So, for example, today we are here, right? So here it says no lab. No lab, no lab, right? Now your lab 2 will be released on 02/18 and it will be due on 02/25, right? So on 02/18 you can go to the lab and you can work on the lab 2, right? On 02/23 you can go to the lab, you can work on the lab. And on 02/25 you must go and show your work. Okay? Like this is the deadline for showing your work and submitting lab 2. Remember, only submitting your lab work online is not enough. You need to go to the lab. You can go to the lab all these 3 days. And like if you are done, you can show to the TA and you don't go. For example, let's say you are done on 02/18. So you don't need to go to 02/23 and 02/25. You don't need to go these 2 days, right? Or like let's say if on 02/25 the lab 3 is released and you want to work on it, go and you can start working on lab 3. Okay. Are you posting the lecture recordings? If so, where? Yeah, here I am. See, in this tentative schedule, here, if you can see my pointer, I have this video link. See, so today's lecture video is not yet posted. Only slides are posted. Okay. Okay. I think that's all for now, and see you in next lecture. Have a nice day.